Okay, you should know by now, or recognize at least this equation, which is Einstein's photoelectric equation, which relates the photon energy, HF, the work function, phi, and the maximum kinetic energy of the photoelectron, Ke max. It's sometimes quite difficult to understand how they're all related, and we're going to use an animation on the PHET site. It's a really good animation which shows you how you can understand this equation in terms of what's actually going on, and we'll also use it to go through the different parts of the specification to make sure you understand what the relevance of these different ideas are. So over here, let's just explain what this experimental setup is. So first of all, we've got a lamp at the top. We've got a cylinder, a glass cylinder, which is of an evacuated tube. On the left-hand side is the metal called the photocathode. In this case, I've set it to be zinc. And on this side is the anode. And then you've got a wire which links the anode all the way back through an ammeter, a power supply, back to the photocathode. Now we're going to switch on the lamp onto 50% brightness, and I'll explain what's going on. So the lamp is now emitting photons. These photons are striking the photocathode, and some of those photons are able to release photoelectrons, and you can see the photoelectrons are shown as blue dots. And what you notice is that they're moving at different speeds. Some of them take a very short time to cross this path, some of them are going a lot slower. So the fastest ones are the ones with Ke max. The wavelength of the light is important because if we have a frequency that is too low, we don't get any emission at all. So currently it says 280 nanometers. A higher frequency is a lower wavelength. So if I move towards the visible end, you'll see at some point we lose all of the photoelectrons completely. So that's an important part of this theory. The threshold frequency is a particular frequency where the electrons start to be emitted. So we'll go back to our previous value, which was about 218. Now Einstein couldn't measure this. This was a prediction that he made, but it was up to experimental physicists later to actually measure the electron energy. And they did this with a very ingenious setup, which is why we're using this photocathode and photocell. So what we can do is we can measure the maximum energy by making this electrode negative, because the electrons are already negatively charged. So if they move towards something which becomes negative, they get repelled and they start to slow down. So I can do that by making this battery voltage negative, and you should start to see, as I make it negative, some of those electrons make it all the way, but some don't, and they start to head back. And we can keep making this more and more negative until we just stop the electrons from reaching that particular anode. And when we know the voltage that is required to stop them getting there, this voltage is the same as the energy of those fastest electrons. So we know that the fastest electrons had an energy in this case which was 1.4 electron volts. And since we know that the wavelength is given, we can work out HF, the photon energy. The work function is phi, which is to do with the metal, and now Ke max can be determined by knowing the voltage here. So that's one way in which the kinetic energy was measured and how it was then used to verify this equation and confirm it. Part E of the specification says the idea that the maximum kinetic energy of the photoelectrons is independent of the intensity. So we know that we're requiring 1.4 volts to just stop the fastest electrons. Let's see what happens if we were to increase the intensity to 100%, so almost doubling it here. So we'll get many more electrons emitted, but they're still only able to just get close to that anode. And that's because we've increased the number of photons and therefore the number of photoelectrons, but the photoelectrons still only have the same maximum kinetic energy. So it doesn't matter what this intensity is. Part F says the idea that the rate of emission of photoelectrons above the threshold frequency is directly proportional to the intensity. And as you can see, I won't change the frequency, but if I change the intensity down to much lower levels, you'll see that the number of photoelectrons emitted is still occurring, but there are very much fewer photoelectrons being emitted. However, the fastest of those, the ones with the highest energy, are still the same maximum energy as they were before. So by adjusting the intensity, all I'm doing is varying the number of photons arriving at the photoelectrode, therefore the number of photoelectrons. One thing that's very important is part B here says a one-to-one interaction. Now what that means is that, if I just put the intensity back up to quite a high value, what it means is that every electron that was emitted, that's every photoelectron, requires one photon to have arrived at the surface. But every photon that arrives doesn't always produce a photoelectron. So it's really saying that we can use this equation which links one photon with one photoelectron. But it isn't the case that every single photon produces a photoelectron.